Okay.
All right. Good evening and good morning, everyone. So I think today we have audience from different part of the world. Today we will have Josh, who's going to give or deliver his PhD completion seminar entitled Introducing Observation-Based Physics into the WAM Wave Model and Wave Couple Interaction. I think it's quite impressive that Josh is currently only at his 2.5-year mark, and he's already completing his PhD. So I think without further ado, I would like to invite Josh to deliver his seminar, which is about 30 minutes. And then afterwards, we'll have some Q&A from the audience. So over to you, Josh.
Okay. Yeah, thank you. So the title of my talk today and of my PhD thesis is Introducing Observation-Based Physics into the WAM wave model and wave-coupled interactions. So this is a joint PhD between the University of Melbourne and University of Hamburg with collaborations at ECMWF and Helmholtz-Zentrum Herion. So waves, why do they matter? Just to get us all on the same page, we're talking about ocean surface waves. So this is basically packets of energy traveling across the ocean surface. And the ones that we're concerned with are the wind-generated waves. Yeah, why do they matter? Apart from for recreational pursuits, is that they can cause damage to ships, big damage and loss of lives as well. They have all sorts of interactions with weather and climate. So all atmosphere, all domains there, such as the atmosphere, sea ice, and the ocean. And in this diagram, I've got the arrows going two ways, showing that both waves affect something like the ocean, but also the ocean affects waves. So that through this, you can get what's known as feedbacks, whereby some initial disturbance can be either amplified or diminished. So our best tool for prediction of these waves so far is what's known as a spectral wave model. So the basic premise of these wave models is that the irregular water surface can be decomposed into a number of sinusoidal components with different frequencies and different propagation directions. So this is very illustrative here on the left, where you've got just a basic addition of all sorts of waves, and they're combined into the complex wave surface. And the distribution of wave energy amongst those components is called the wave spectrum. So this equation here, the energy balance equation, is the fundamental equation for these models. On the left is the propagation of wave energy, and on the right, what's known as the source terms. So I've got three here, but the list can be infinitely long, but these are the three main ones. So we have a term for wave generation through wind input. There's a term for nonlinear wave interaction. So this is basically a redistribution of energy between the various wave components. And there's also a term for dissipation, mainly due to whitecapping or breaking. The observation-based wave physics, which is a feature of the talk, is a method of representing the first and the third term here. So the input and the dissipation. And this, the approach for this observation-based wave physics was to measure these source functions directly, or at least as directly as can be done. So through this approach, various physical phenomena can be represented or included here, such as nonlinear airflow separation, the steepness-dependent wave growth, negative wind input under adverse winds, two-part wave dissipation, wave breaking threshold below which no breaking occurs, and swell decay due to interaction with and production of oceanic turbulence. So where is this observation-based wave physics? There's three dominant wave models, spectral wave models globally. which is SWAN, WaveWatch 3, and WHAM. And so far, this observation-based physics is in SWAN and WaveWatch 3, but not yet in WHAM. So that is the focus of this first part of the talk, implementation into WHAM. So as I said, it's already in WaveWatch 3. And my approach here was to, as much as I could, more or less follow the logic of the coding of the observation-based physics in WaveWatch 3, where it's called ST6, and transpose this over into WHAM. So I've just got this diagram here just to kind of give a taste of the implementation, which is a lot of code. So I've used this logical switch iFiz equals 2. And when you switch this to 2, you get, it follows this new logic train where I've got a module for the S input term, a module for the stresses and fluxes, one for the dissipation, and another module specifically for swell dissipation. So after many iterations to flush out all the bugs and convergence on a final code, I test it using a 1-year hindcast simulation in one-way coupled mode. And then we assess, so this is a global simulation. And then I assess this against observations from the wave buoys for both wave height and peak period. And on the right here, I've got a regression analysis for wave height on the top and peak period on the bottom. And yeah, particularly for wave height, as you can see, it looks quite good. For peak period, there's a bit more scatter, but I state here that its performance is similar to operational standard. And yeah, for peak period, the wave models generally have a more difficult time to predict that. So it's in the wave model WHAM, it's looking good, and it's got a reasonable performance. So yeah, so now it will be available in future public releases of WHAM. If you'd like to read more on this and the implementation and some more analysis, you can see our OMAID 2022 paper. So the observation-based physics is concerned primarily with the open ocean. So it neglects coastal processes and polar regional processes in the polar regions. The polar regions comprise a considerable part of the global oceans. So, and that beyond that, they're also very important for what sort of changes we expect to see over the coming century with regards to climate change. So it's a very important region, and here we extend this observation-based approach to the polar regions. So you're a wave, you reach the polar region, what happens here? So I've got a video to have a look. Mm-hmm. Yeah, it's 10 minutes. It's a great video, but I can't show it all. But I'll tell you what's happening in it. So the waves, as they enter the sea ice, the further they go, the smaller they get. So this is called attenuation of waves by the sea ice. So they're getting smaller. And the way that this can be represented within our spectral wave models is we add another term, another source term to the right-hand side of this equation. And a big question, and it's a very active area of research at the moment, is how do we best formulate this source term, S-ice? So to answer this, we should consider what are the dominant processes in attenuation of waves by sea ice. One of the main ones is viscous attenuation. So this is energy loss due to collisions between ice particles. And so the energy is lost from the waves and goes into these collisions. As you could also imagine, the state of the ice itself can also be very important. So here I've got a few pictures of some ice. On the left here is a solid ice sheet. Effectively on the right is what we've seen in the video, which is known as pancake ice. And as you could imagine, the waves would have a much harder time of going through this solid ice than through this pancake ice. So here are some observations of that from a ship for these ice conditions. And you see when the ice is solid, you've got what's known as blocking. So the wave signal is completely blocked or attenuated by the ice. And then as the ice breaks up, you start to see waves of 3 to 4 meters. So it's clear that they can propagate through the ice much more easily when the ice is broken up. What complicates this situation even more is that the waves themselves can be the cause of the sea ice breakup. So here I aim to formulate a new formulation for this S ice term. So I begin with a relatively standard attenuation of waves by sea ice model, and I include an observation-based threshold to identify when the ice is broken by the waves. And then when this happens, I decrease the attenuation in this model. So decrease it for the broken ice by this range supported by observations as well. We have observations for that. And this is somewhere between factor 10 and 100. So attenuated less for the broken ice. The additional novel features that this representation brings is that it represents the state of the ice field, so unbroken or broken. And it also features two-way coupling between waves and sea ice. And that therefore allows these feedbacks that I mentioned earlier to come into the system. So I test this new formulation for this S ice term in a case study. So this is a case study of the Davis Sea, Antarctica, for the Antarctic summer of 2019-2020. And this is done within a global spectral wave model with a high resolution domain for the Davis Sea. So that's pictured here. And we're using high resolution sea ice concentration from the satellite observations and high resolution winds from ECMWF's archived forecast to force the model. So this way the model is as best informed as reality as it can be. And then the results from the model is validated using drifting buoys for the waves and satellite imagery for the ice. So I mentioned these drifting buoys, and the validation here is using these drifting buoys. So we want to know, are they actually in the ice, and are we actually validating for waves in the ice? So here's the broader domain, and you see here's the Southern Ocean above, and these regions of mid blue and dark blue indicate firstly 15 to 85% sea ice concentration, and then above 85% sea ice concentration. And these lines here show where the buoys are. So you can see that the whole time they're in this 15 to 85% sea ice concentration area. And additionally, they're also protected from the Southern Ocean by this ice barrier here. So this is to show that the wave buoys themselves are definitely in the ice. So how well does the model do for predicting or simulating the waves at these buoys? So I've used the model here to simulate a physical range of behavior based on the likely ice properties. And that's what you see in these colors here. That's the physical range of the model. And this is wave height following one buoy. So it's a time series. And what we see is that the observations from the buoy, shown by these crosses here, essentially all fall within the physical range given by our model. So it looks quite promising for for wave height. And also if we look at the spectrum, which I mentioned earlier, so this is a snapshot of one spectrum, we see that the observations more or less fall directly within the center of this physical range. So the model also does quite well at simulating the wave spectrum in sea ice. And so that was what happened to the waves and how well the model does for the waves. But we're also concerned with what happens to the sea ice in our model. So as I said, the sea ice in the model is broken up by waves and only waves. And we start with a field of solid sea ice, and then this is progressively broken up. And that's characteristic of this season where it's the melt season. So you're not really getting too much formation of new ice. So in this plot here, there's basically the number of solid ice grid points, and this is time on the x-axis. So as our study period moves along, we're losing, or the ice in the model is breaking up. What's interesting is to look at the spatial and temporal nature of this breakup and how well this actually does compared to what we see in the satellite images. So in this figure on the right, I've overlain our model results onto the satellite images when we had clear days. So these blue dots represent the solid ice in the model, and then where there's no blue dots, it's broken ice. So this red line shows the front of where we've got solid ice, and this is the 10th of January, and as you move, so I say at the 10th of January, what we see in the satellite images and what we see in our model quite well matches each other. So we've got solid ice in the model and what looks like solid ice in the satellite imagery. And as we move forward 2 weeks, there's significant breakup of the ice sheet in this region here, as we see in the satellite images. And we also see the same breakup happening in the model at the same time. And then when we move forward another 2 weeks, we lose a big chunk of ice in this region here, and the model follows the similar breakup. So as I said, the breakup of the sea ice in our model is only by waves here, and it looks like it matches what we see in the satellite imagery quite well. And this provides quite nice evidence that the breakup of sea ice in reality is a wave-dominated process. And this is opposed to some argument in the literature that it might be other physical processes such as wind that can drive this sea ice breakup. So if you'd like to read more on this work, we've got a paper in JGR Oceans, which also gives more information on the model details. So I'd like to flash back to this slide of our observation-based wave physics and highlight this last point is it concerns swell decay due to interaction with and production of oceanic turbulence. So just to give a bit more background on what's happening here is the waves interact with the underlying turbulence in the ocean, and the energy is lost from the waves, but it has to go somewhere, right? So it's converted, well, it goes into turbulence and it's converted into these turbulent vortices in the ocean. And this interaction that leads to that conversion can be significant up to depths of order 100 meters. And this additional turbulence that you get due to the swell decay can be an additional or a considerable source of mixing within the oceans. So for this next part, we're taking this additional source of mixing from the wave turbulence interaction and putting it into an ocean general circulation model, which is NEMO. We achieve this through adding an additional term for production of what's known as TKE, which is turbulent kinetic energy, within the TKE scheme. And in an ideal world, we'd put this into the model and the model would get better because this is something that the model's missing, except it is never so easy. So some time ago, maybe 10 years, NEMO was diagnosed with a too shallow mixed layer. And in order to rectify this, there's been a nice solution introduced where basically you insert additional mixing into the NEMO model where there's not enough. So on the right here, there's a map of basically how much additional mixing has been put into the model to address this bias. So this is by Rogers et al. And you see red indicates a lot of mixing, and then these purples is minimal. So there's been a lot of additional mixing put into the Southern Ocean, and then also in the Northern Hemisphere storm belts, we've got quite a bit of additional mixing going in. Yeah, and so we propose here that perhaps why this additional mixing is needed is that it's missing some key physics. So perhaps this wave orbital induced turbulence that I mentioned in the last slide. So then there's motivations for the introduction of this into NEMO. One is that you're introducing missing physics, and two or more research-driven motivations is what differences, if we include this, would we then see in mixing, and can it improve the model performance of NEMO? So we run two NEMO ocean simulations. One is a control where you've got this additional mixing parameterization on. And the second is the wave mixing run, where we turn this Rogers et al. Parameterization off and add mixing due to wave orbital induced turbulence. And these are both 30-year simulations at a 1 degree horizontal resolution. So a common diagnostic for how much mixing we see in the models is mixed layer depth. And on these figures on the left here, we've got red indicating an increase in mixed layer depth for our new wave mixing simulation, and blue indicating a decrease. And what we see for the December, January, February months, we see essentially a global increase in mixing, particularly in the Northern Hemisphere storm belts here. And then for the June, July, August months, we see it's dominated by this decrease in mixing in the Southern Ocean. And note here that the scale is double what you see in the DJF months. So up to 22 meters shallower mixed layer depth for our new simulation. And this figure here effectively shows the yearly climatology for the Southern Ocean region. And the orange line is our new wave mixing simulation, and the blue is the control. And this black line here is the observations. So you see, if we start with this shallowing that you see in the summer, you see it brings it closer to the observations, and also the deepening that you get. Sorry, that's the winter months for the Southern Hemisphere. And this deepening that you get in the Southern Hemisphere summer also brings it closer to the observations. To show you another region, the Northern Pacific, you've got a year-round deepening there, and that also brings it closer to the observations. So that was what differences we see in mixing or mixed layer depth, but also interesting is what differences we see in temperature. So here I've got red indicating warmer temperatures for the wave mixing simulation, and blue indicates cooling. And this is a cross section of the global ocean. So there's the South Pole here, the North Pole here, and this is depth on the y-axis, and all longitudes are considered here. So it's averaged across the whole globe. Yeah, and what we see is generally a warming throughout much of the global ocean for the December, January, February months. with an exception being this cooling in the Southern Ocean in the mid-depth range here. And for the June, July, August months, we see quite, most regions have a cooling at the surface, and this cooling signal that we had here in the Southern Ocean extends the full depth of this upper 200 meters. And this warming here persists. So perhaps more interestingly is how this compares relative to the observations. So this is the same plot as before, but now for root mean square error instead of absolute difference in temperature. And we see that it's mainly blue. So this is a decrease in error for our new wave mixing simulation, with the big exception being the high latitudes in the Southern Ocean. And this is what it looks like from the top, so a bird's eye view. And on the right here is the yearly climatology of this error. And again, the orange line is our new simulation. And so in the average, it decreases the error by about 1% for the upper part of the ocean temperatures. Okay, so that brings us to the summary. So firstly, the observation-based wave physics was implemented and validated within WAM. So it's all in there and working, and it'll now be available in future public releases of WAM, therefore to a wider audience of research and practical communities. Then extended this observation-based approach to the polar regions and tested a new formulation for this S-ice term, which is wave-ice interaction in an Antarctic case study. And this formulation well represents waves in sea ice, but also what happens to the sea ice as an effect of waves, or due to the effect of waves. And it establishes that waves are the dominant process in the sea ice breakup here, as opposed to wind, for example, at least in our case study here. Lastly, we took this part of the observation-based wave physics that's due to wave-ocean interaction and put it into the NEMO ocean model. And we saw that the new ocean model scheme achieves an ocean state that's more consistent with observations, both in mixing and in temperature. And it shows that maybe NEMO and likely other ocean models are missing some important wave-related physics. And neglecting such physics may lead to biases, which are often addressed by non-physics-based solutions. So such as that Rogers et al. Solution I showed you before, which is very effective, but it's non-physics based. So the waves can be a better solution to this sort of bias here. And here's the references, if you guys would like, and I'll leave it on this slide. So thank you very much all for attending and listening.
Thanks, Josh, for the seminar. I would like to now invite questions from audience. So I think those questions from supervisors may be, okay, yep. Ian, I saw a hand from Ian. Ian, would you like to ask your question?
So, Josh, it's really a question of detail. When you implement the BY-DBR physics in WAM, what do you do with U star? Because I mean, I guess one of the characteristics of WAM, as I understand it, is sort of Peter Janssen's U star relationship being dependent on the tail. Mm-hmm. And I could sort of imagine implementing the physics, but keeping that relationship between U10 and U star. Is that what you do, or do you go to something more like as in WaveWatch?
Yeah. So for the first implementation, as I've got here, it's essentially what is in WaveWatch. So it's it doesn't have this complex air-sea coupled nature within it. But yeah, in the future development, that's going to be the focus of this, is actually to make it operate in a coupled sense. But yeah, it just uses the basic drag formulation at the moment.
Yep. Okay, thank you.
All right. I'm not sure who raised his or her hand first. Joanna, did you raise your hand first?
I'm not sure who was first. I never counted, but since you gave me the word, thank you, Josh, for the great presentation. I was just wondering for the study of the observation-based physics that you implemented and compared to the other physics, namely the one of Janssen, so-called in WaveWatch ST3 and Arduino ST4. Have you compared your results against satellite data, and are there improvements in the skill?
I haven't got the chance to look at the satellite data yet, no. So that that initial comparison was only with buoy data, and yeah, the satellite data, actually I'm working on that at the moment, is yeah, to have a proper framework in which we compare satellite data both from wind and waves. Yeah, and also, yeah, so the altimeter data is the classics, but I'm also looking at a comparison with the scatterometer data as well at the moment.
Thank you.
Next. I mean, Joanna, you're happy with the answer?
Yeah, thank you.
Yeah, all right, okay. Yeah, I think Joanna. Yeah.
I had raised my hand, so I don't know in which order it's going. In the formulation to replace this ad hoc extra mixing needed to NEMO, upon the, yeah, I like the result obviously, but I could argue, you know, you bring a field that contains seasonality, because the waves have a seasonality. Could the Roger R be modified to add a seasonality that would give similar impact?
Yeah, quite likely, I think. Yeah, I think that's one of the big benefits that bringing waves brings. So yeah, the Rogers et al. Parameterization effectively brings a yearly mean of what effect the waves would be. And yeah, you could add, so they've done a latitude dependence on it, which is a start, and then to make it more complex, you could do a seasonal dependency. But the more complex you go, it would almost just be better to go straight back to the root of the problem, and instead of trying to do this ad hoc adjustment or model tuning, you can implement the real process, perhaps, that is the reason why we have this bias in the first place.
I can see Joanna is raising your hand again. Do you want to ask a follow-on question? Yes.
Yes, actually, I wanted to ask a question also related to the wave-induced mixing into the NEMO. And as far as I understand, you induce it into the TKA scheme. You know that in NEMO, state-of-the-art, especially within the operational community, they're using GLS scheme, and there is also osmosis parameterization that is considered into it, as well as other wave-induced processes, namely state-dependent momentum and energy fluxing introduced into the system as Stokes-Coriolis forcing. So could you please comment what is the added value in that parameterization in respect of what is into the state-of-the-art in the existing NEMO code? And if you introduce that, isn't it a double counting, or it is an alternative to one of the existing versions? It is just understanding how your mixing scheme works.
So, yeah, so with these other non-TKE based schemes, the wave mixing could be introduced, but yeah, it would likely be a double counting, because as I understand of something like this osmosis scheme is that they aim to get the right mixed layer depth based on observations as well. And I don't know the details of it, but there's a lot of physical justifications for it. And I think if you just added mixing due to this swell decay, then it would throw out the whole scheme. I would say though that they wouldn't be including this process, but they might be including it kind of implicitly, so they know how much mixing is needed. And it might be in the physical justification, it might be tied to wind or some other wave related process, but yeah.
Thank you.
So I was struggling here to raise my hand.
Yeah, I thought I saw a thumbs up from you. Sorry, Alex, go ahead. I saw, okay. Alex first, yes. I saw another raised hand. But Alex, you can go first.
I don't have questions, so because obviously I know the thesis, right? Just wanted to add a little bit to a comment, right? Add to the discussion, right? Josh basically answered all those questions, right? That which he was asked, right? I just wanted to kind of highlight the fact that he's trying to add physics rather than new parameterization, right? It's like, Jean, can this approach of Rogers et al. To include seasonality? Of course it can, right? If you know what you want to achieve, the result, right? You can tune to that, right? But then it will be tuning to what you already know. And when something will be unexpected, like you use NEMO for whatever, for weather patterns or for trends or for climate change, right? Then your tuning may not work. Whereas if you just add a mixing, a wave mixing, and then you model the wave mixing in the future climate, then it should work always, right? And that's the same with the parameterizations, as Josh said, right? Is if there is already parameterization for the turbulence in the ocean, which is connected to the atmosphere somehow, to the winds, through the winds or somewhere, but is actually produced by the turbulence, then it accounts the effect on average, right? On average it works, but when the winds are stronger, the waves are bigger, it will underestimate the mixing, and when the waves are weaker, they will overestimate them, right? So these parameterizations, they can be tuned, but then they will not work outside of the conditions for which they were tuned. Whereas in K epsilon scheme, you don't do the parameterization. You add this energy which comes from the wave dissipation into the turbulent production term. It's the fluid mechanics equations, and then they take care of themselves. Sorry, Josh, that wasn't. I was just elaborating on your answers.
Yeah, no, that's very helpful. Thank you. Yeah.
Josh, I'd raised my hand to make a common question, but Alex kind of say the same thing I wanted to say. So I don't have a one on that one, but I may want to make a common question of see your views on this on the different aspects. So the ice breakup, I think the community, the wave model, the sea ice modeling community has realized from research like yourself and others that ice breakup due to wave impact is a real thing and should be modeled. The problem, you can say you add this, you break the ice, but we know that ice can also refreeze. What is your view, if we pursue, as I think we should, doing this coupling with an active ice, well, an ice model at least and a wave model, because this goes hand in hand. Do you feel that ice model has evolved enough that you will not just essentially pulverize the ice, and at the end you end up with just no ice because you will keep getting waves, and then there's a positive feedback, more waves, more destruction? Do you think the ice model can cope with it, or there's something still underneath that we don't know that we may have to discover the hard way?
Yeah, that's a great question. And to be honest, I would have no idea until I see it put in there. But from what I've seen from some simulations of like ice model refreeze and breakup, from this there's this phase-on ocean sea ice coupled model, and also got waves in there. From what I've seen, it looks realistic, like this sort of thing where you see they've got this ice sheet, which then might be broken if you've got like in this model, you've got it breaking by the ocean current. So it's because of these stresses, and it has to break up. And then when it breaks, you get these big cracks formed in the ice. And then those cracks persist for some time, and then they refreeze. So it looks like that they are able to represent this, like this breakup and then refreeze. And yeah, I don't know, for when you introduce waves into that, I'm not sure. My impression is that the waves should just break the edges of the ice first, and I don't think they'd. I don't know. I'd have to see it, but I get the impression they wouldn't be able to just straight away remove the whole ice sheet, because yeah, I think, as you say, if they did do that, then it could melt pretty quickly. But yeah, it's something to. It's a good research question, definitely.
I can see Alex has raised his hand, perhaps to add on to the discussion.
Yes, so I can't resist, because it's an interesting discussion, and it takes us a little bit outside of the topic which Josh was doing, right? Josh modeled how the waves can break the ice, and when I first saw these pictures comparing the outcomes of his results with the satellite observations, it was just striking, right? His contours coincide with what satellite sees, right? So he can predict how the waves break the ice. That is based on the ice properties, right? It's the ice thickness, the ice elasticity, the wave height, and so on, right? Obviously, he cannot predict whether the ice will melt or it will refreeze, because that depends on the temperature of the air and of the ocean, right? That is not part of the wave model. So it has to be fully coupled, right? If the air is warm and the ice is broken, the ice will melt, right? Because you decrease the albedo, you expose the dark water, and the water will start moving, warming even faster, and it will melt. But if the air is very cold, which is the autumn condition, right? The waves will still break the ice if it's the waves are of appropriate height and the ice of appropriate thickness. But what follows that, right? Once the storm subsides, right? Depends on the air's interaction model, right? So it's no longer the wave model. And we did model Arctic on the different projects and with different models, right? The ice does refreeze, right? And the ice cover actually increases, right? Because after the waves break the ice, it spreads over the larger area. And if the air is very cold, it refreezes. But that depends on how good your atmospheric model, module, right?
It sounds like this could be the next project.
Yeah. Well, it's a lot to do.
Yeah. I can see we still have maybe a few more minutes. I would like to ask, do we have any other question from the audience? I noticed that the Spoisers has been very active in asking questions. Perhaps we have any from general audience? I have to say that it's a very interesting talk for me, especially coming from geotechnical background. Perhaps I just have one concluding remark if there's no other question, or any last one from supervisors? Everyone is happy? Yep. So I think, Josh, thanks again for the fantastic seminar. And this, I think we all will look forward to the next release of the WAM model that have your implementation. So I would like to put my hand, I mean, this is a virtual one. So I'd just like to thank your presentation. So what I would like to do next is, after closing this seminar, can I please ask all the panel members to join a separate link